Hello, let's continue our discussion about basic mathematics that is required for machine learning. One of the important topics in machine learning is probability theory. I will give you some of the basic concepts of probability theory so that you can understand some of the uh, inspirations behind machine learning models from the probabilistic standpoint. To give you a brief intuition, uh, concepts such as probability of making a correct prediction, probability that your prediction is closer to the correct value. Those are some important concepts in machine learning. So a lot of machine learning is heavily based on probability theory. So with that introduction in mind, let's start with the very basic concept in probability theory, which is that of a random variable. Uh, so we will describe these, we will use this notation of capital letters for random variables. So a random variable is a variable whose value depends on some random phenomena. Uh, that is, you can also call it a random event. So a random event happens, and then you can encode that random event using some value, and that value will be given to the random variable. So the value itself, for that we will use the small letter. So let's take a concrete example. Let's say we are tossing a coin, and the events can be heads or tail. Okay, so the event outcome can be either head or tail. Okay, so this is your event space. Okay, we can encode this, and let's say we encode it into 0 and 1. So head being 0 and tail being 1. So basically what we can say is that this random variable belongs to this set 0 and 1. Okay, now this event space defines different events, and together these events are mutually exclusive and collectively exhaustive, MECE, right? So you can think of, in terms of Venn diagram, you can divide the entire event space into two different buckets. One is 0, the other is 1. Okay, so they both add up to probability of 1. So basically, if you have a fair coin, so fair coin means that if you look at it from the side, and this is head and this is tail, then it will look like a rectangle. And for that fair coin, probability x is equal to 0, capital X is equal to 0, is equal to probability, or it is equal to 1 minus the probability x is equal to 1, and both of them are 0.5. Okay, you can also have a biased coin. Okay, in which case, let's say the side view of the coin will not look like a rectangle, but it will look like a trapezium. So let's say this is the head, this is a tail. I mean, this is an example of a biased coin. So as you can imagine, that it is more stable when it lands tail at the bottom and head on the top, and it is less stable when it lands the other way around. So the probability of having head on top is going to be higher. So this probability of, let's say, x is equal to 0 can be greater than 0.5. So let's say it is 0.6. Then probability of x is equal to 1 is going to be 0.4, because the two outcomes are possible outcomes are mutually exclusive and collectively exhaustive. Their probabilities add up, and they add up to 1, and the probability of any of these events happening is always going to be greater than equal to 1. Okay, so greater than equal to 0, p of x is equal to x for all x. Okay, for all x is greater than, or let me put it this side, for all x is greater than equal to 0, and then sum over all x, p of x is equal to x is equal to 1. Alright, so you cannot have two different outcomes for the same experiment, and that's just by definition. So here you can see that this adds up to 1. So basically this leads us to a very related concept, which is probability mass function, and basically that is a mapping of all the possible outcomes of a random variable to the probability of them happening, right? So basically what we have here is that p of x, right, uh, p of x is equal to x, right? Another way to write this is p and then small x here, sorry, capital X here, and small x in the bracket. So here what we are saying is that this is the probability of this variable, random variable capital X, and small x are the values. So this function is called a probability mass function because it maps x, okay, to real numbers, or actually it maps them to this set from 0 to 1. Okay, the probability can never be less than 0, it can never be greater than 1, such that, okay, p of x summed over all x is equal to 1. Okay, so this mapping is called a probability mass function. So one way to depict this would be that we show this using some sort of a bar chart where you have two different values. You have values 0 and 1, and 0 can have, let's say, 0.6 value, and this one can have zero point 0.4 value, right? So these are the two different possible, these are the two different probabilities of the biased coin, for example, and if they are equal, then it is an unbiased coin. Similarly, if you have a dice, then perhaps your encoding is such that you have 1, 2, 3, 4, 5, 6. Okay, so you will have, let's say if it is a fair dice, then each of them is 1 by 6. Right. So notice that because it's a discrete random variable, this x is a discrete random variable. We haven't talked about continuous random variables yet. So here the what you're drawing is a probability mass function, and you're drawing it as a bar chart. When we are talking about continuous random variables, we will show that as a continuous curve, because the x-axis is also going to be continuous. Let's talk about some common probability mass functions. The first one is what you just saw. It's the uh, Bernoulli probability mass function, and we define this using a parameter mu. Okay, we can call it mu capital X. Alright, so what is mu x? So that is the probability that the random variable will take value 0. Alright, so this is going to be an O. So here this is for a variable x, where this x belongs to 0 and 1. Alright, so with this particular probability mass function, there are a couple of things we can do, right? So one thing that we can do is we can define the expected value of x. Expected value is similar to a weighted mean. Okay, so we can do expected value of x. So it's a stylized e. The symbol is a stylized e, and then within parenthesis we'll have x. Alright, so expected value of x is always, the formula for this is going to be sum over all values of x, okay, then x times p of x. Right, so if we apply that, so what is mu x? Mu x is the probability that x is equal to 0, right, which is equal to mu x. Okay, mu, I'll just use small x here just to avoid confusion. So here, what is this going to be? We can take two values, 0 and 1. So it is going to be 0 times uh, mu of x plus 1 times 1 minus mu of x. So let's talk about probability mass functions, some common probability mass functions. Um, so the first one that we will talk about is what you have already seen, which is Bernoulli. The name for that is Bernoulli, after the scientist Bernoulli. Uh, Probability mass function. So basically it is defined for a variable x that belongs to either 0 or 1. It can take value 0 to 1, and it is defined by a parameter mu, and this parameter is, let's say, this is equal to probability that x takes the value 1. Okay, and it will be something, so this mu belongs to this interval 0 and 1. This parameter cannot take values outside of this interval. So what is your distribution? Your distribution, this Bernoulli distribution for x given mu. Okay, this line is called given. Okay, is going to be mu to the power uh, mu to the power x and 1 minus mu to the power 1 minus x. Now let's think about this for a minute. This is same as writing, okay, this is same as writing is equal to mu if x is equal to 0, okay, is equal to 1 minus mu if x is equal to 1. Okay, so this same expression can be captured succinctly using this. So whenever you have a binary variable like x, x in this case is a binary variable, you need not write if then else. You can simply write it as a power. Okay, you can simply write the variable and 1 minus that variable as powers. So this is a mathematical trick that you can use for binary variables. It will come in handy later, so keep that in mind. Okay, so now with this uh, particular uh, probability mass function, we can define something called expected value of x. This is a stylized e, expected value of x. What is expected value? It is similar to the concept of a weighted mean weighted by the probabilities. So this is going to be, by definition it is going to be sum over all values of x, okay, x times p of x. Alright, so let's see what is that going to be. For the value 0, it is going to be, what is it going to be? 1 minus mu, I'm sorry, here I made a mistake, this should have been 1 and this should have been 0. So 1 minus mu for 0, and then here if the value takes 1, then it is mu. So this is equal to mu. Okay, so this is the expected value of x. Now we can also think about expected value of any function of x. Okay, so the expected value of any function of x, f of x, is equal to sum over all values of x, f of x, p of x. Alright, so this is going to be equal to f of 0 times 1 minus mu and then f of 1 times mu. Okay, it could be any function. Here the function happens to be x. Now let's talk about another function. Let's say we take the function x square. expected value of x square. Okay, so that is going to be 0 times 1 minus mu plus uh, 1 times again mu, which is equal to mu. Okay, so why am I talking about expected value of x square? Because now I can also compute variance of x. So what is variance of x? Variance of x is uh, the expected value is equal to the expected value of x minus expected value of x whole squared. Okay, so what is that going to be? That is going to be expected value of x minus mu the whole squared for Bernoulli distribution. Okay, so now if I look at that, this expectation operation, because it is based on this summation, it is a linear operation. I can basically say that this is equal to expected value of x square minus 2x mu plus mu square, and it will basically become expected value of x square minus expected value of 2x mu minus plus expected value of mu square. Now mu is a constant, right? So basically this becomes expected value of x square minus 2 mu expected value of x, okay, and plus mu square. Let me draw a line so that it's easier. Let me draw a line of a different color so that the mess is resolved. Mu square. Okay, so what will this be? So we know that expected value of x square is mu. We know that expected value of x is mu. So basically it becomes so the first term becomes mu, the second term becomes 2 minus 2 mu square, and then you get plus mu square. So basically it will come out to be mu minus mu square. Mu minus mu square, which is same as mu times 1 minus mu. Okay, so this is the variance. The variance of a Bernoulli distribution is mu times 1 minus mu. Okay, so we saw how we can calculate it from the first principles. All right, so this is the first common PMF for discrete random variables. The second common PMF is the binomial distribution. Okay, so if so this binomial distribution has two parameters. The first is mu and the second is capital N. Okay, so what is a binomial distribution? It is basically saying that what is the expected value of a binary random variable which with values 0 and 1, where each random variable itself so you basically take n instances of that random variable, and those all of those events that you get for that binary random variable, they are IID. So what is IID? It's a very important concept. It is independently identically distributed. So think about a coin toss. The coin can be biased, but you do let's say 3 tosses. Okay, so those 3 tosses are independent of each other. They are identically distributed. That means the outcome of getting a 1 or a 0, let's say the outcome of getting 1 is equally likely in the first toss, the second toss, and the third toss. But they are independent of each other, and they are independent of each other. So if they are independent of each other, then we want to describe the sum of the three coin tosses. Okay, so we can either get 0 0 0, we can get 0 1 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, and 1 1 0, 1 1 1. Okay, so here the sum is going to be 0, sum is going to be 1, sum is going to be 2, sum is going to be 1, 2, and then it's going to be again 2 and 3. Okay, so what is the event space here? In the event space you can have 0 1 2 or 3. Okay, and so we want to now describe what is the distribution of getting 0 or a 1 or a 2 or a 3. So we want to draw this graph 0 1 2 3. We want to find what is the height here, what is the height here, what is the height here, and what is the height here. Okay, so as you can see here, the and then this may not even be a fair, the coin itself may not be a fair coin. Mu need not be 0.5. So what if mu is not 0.5? Then what does this distribution looks like? So here let's call this variable y. Okay, so the binomial distribution of y given mu and n, this is what we want to define, and you can find it very easily. You can think about it very easily from uh, thinking about all these events, that it is going to be n choose y. Okay, mu to the power y 1 minus mu to the power n minus y. So this is y. Okay, y can take values 0 1 2 and 3. Okay, so this symbol that you see, you might be used to looking at it as n choose y, like this. It's the same symbol, it's the same quantity, it's just a different symbol. So for such a random variable, expected value of y is going to be n times mu. Try this out, how it comes out, and you will find that it will be n times mu. Okay, similarly you can find variance of y and so forth.